Hi guys, Miss Malik here. We're up to exercise 5H, which is the last exercise from chapter 5. So well done on getting to this point. Here we're looking at exponential growth and decay. So the question that we're going to deal with first is the following. A bank pays 10% interest compounded annually. You invest $1,000. How does this $1,000 grow as a result of the interest added? So we have a formula for finding compound interest, and that is A equals P times 1 plus R on 100 to the power of N. So we need to know that P is the original investment amount, A is the amount the investment grows to after N years, R is the compound interest rate in percent per annum, and N is the number of years you invest for. So for this one, A equals 1,000, because that's the original investment amount, $1,000, times 1 plus 10. 10 is R, and 10 is 10%, divided by 100, to the power of N, and N is the number of years. So it's A equals 1,000 times 1.1 to the power of N. And what that means is that for any number of years, you just need to substitute that into N. So the question asks us, how does that $1,000 grow as a result of the interest added? You could substitute in a few values for N, maybe 1, 2, 3, 4, and 5. That way you can show how it's growing over the 5 years. Remember that compound interest is different to simple interest. Compound interest means that at the end of the year, you get interest on the amount that's in your account. So after 1 year, you get interest. Just say you got $100 interest. So then you would, for the second year, get your interest on top of your original amount plus the $100, and so on. Simple interest just is calculated from the original amount every time. Here we look at the population of a town that was 8,000 at the beginning of 1992 and is then 15,000 at the end of 1999. We want to assume that the growth is exponential, and we want to find the population at the end of 2001. Here I've listed, I've given an equation here, which is A equals 8, 0, e to the power of kt. That's how we find exponential growth and decay. That's the equation we used. So A0 is the constant, and in this case, that's 8,000. That's what the population was at the very beginning. K is the growth or decay. You would hope that the population is growing rather than decaying, because then people would be dying off. In this case, we're talking about more people being born. So K equals, well, we want to find out what that is. The time in this case is 8 years, because we're going from the beginning of 1992 to the end of 1999. And A is the quantity at time t. So A is 15,000. So if we substitute in our values, we end up with A being 15,000 equals A0, which is 8,000, E to the power of 8 being T, times K. K is 1/8 log E, 15 on 8. And K therefore is 0.079. I've solved K by just rearranging my equation 15,000 equals 8,000 E to the power of 8K. I approximate K, and I make sure that I put the squiggly equal sign, because K does not equal 0.079. It's approximately 0.079. That's important. That means that K is 7.9% per annum. Therefore, when T is negative 10, P is 17,550. I found that by just substituting K in. Now, let's look at the second part, and that is, in what year will the population be doubled that of 1999? So there's my formula there, A0 being the constant of 8,000, K being the growth or decay, which we solved for 1/8 log E, 15 on 8, and T being the time. That's what we're trying to find this time. A is the quantity at time t, which is 30,000. Let's sub that in. So 30,000 equals 8,000 e to the power of 0.079 t. Let's solve for t. I divide 30,000 by 8,000, which gives me 3.75. And then I find E, or T rather, by doing 1 over K log E 3.75. And therefore, 16.82 years after the beginning of 1982, that's when the population will be doubled. And that we have to say, well, that would be in 2008. And that's all. That is the end of chapter 5. Well done on completing that.